3.6 is all about undoing derivatives, the inverse operation of a derivative, which we're temporarily just going to refer to as an antiderivative, and later we're going to refer to as that process being called integration when we spend many more chapters looking in depth at that idea. But just for starters, read through A through F, pause the video, kind of look through and get an idea. Think about if you take the derivative of each of those functions, what do you notice about the result? So go ahead and pause the video and do that for A through F. So for A, B, C, all of those functions, when you take the derivative, give you the same derivative, which is cosine of x. And part of this should make sense, right? The derivative of a constant is nothing, is 0. So it does make sense that if these functions are only different by a constant, it makes sense that the derivatives are all exactly the same. But thinking about that in reverse, if you actually started with the derivative, if you knew that the derivative was cosine of x, what could you say about the original function? You could say that the original function, again, we're kind of thinking backwards here, the original function would have been sine plus potentially some constant, which could have been -2, it could have been 11, it could have been 0. Now, if you look at D, E, and F, the derivative for each of those functions is 15x to the fourth. And again, the original functions were the same with the exception of their constant. So thinking backwards, if I told you the derivative of some function f is 15x to the fourth, what could you tell me about the original function? You could tell me that the original function was 3x to the fifth plus potentially some constant value. And that idea is something I really want you to keep in mind when we start talking about anti-differentiation. So anti-differentiation, which we will later call integration, is the process of determining a possible function whose derivative is known. A possible function whose derivative is known. However, when finding an antiderivative, we can't be sure we're finding the exact function unless we have more information, which is why we always include a plus c when we are doing this. We always include a plus c because there could be any constant added to the function that when we take the derivative disappears. So we will write that as f of x plus some constant value c. So for these first 4 problems, we are given the derivative, and I want you to think about the rules that we know, the power rule, the derivatives of sine and cosine. I want you to think about those things to try and work backwards to get back to the original function. So go ahead and pause the video and see if you can get back to the original function, thinking about those rules and working backwards. So looking at number 1, we know that when we take the derivative, we move the exponent forward. So originally, and we subtract 1. So originally this was x to the third power because it's now x to the second power. So we have to figure out that 3, if this was originally x to the third and we differentiated to get 3x squared, that would give us this value. So again, you're thinking through, how would I undo this? What's happening to the exponent when we take the derivative? We're subtracting 1. So when we're doing anti-differentiation, we're going to add 1. Then we need to make sure, and we could check this, if I took the derivative of x to the third, yep, that would in fact give me 3x squared. And don't forget your plus c. Number 2, I'm going to rewrite that as x to the negative third power. So thinking through that, if I took the derivative to get here, I would have originally subtracted 1 from the exponent. To find my new exponent, I should add 1. Well, if I add 1, that would be -2. But then if you think about that, if I just had x to the negative second power and I moved that forward, then I would have -2x to the negative third power. But looking at this antiderivative, I don't have that -2 in front. So in order to get rid of that, I need to divide by -2. So that's where this 2 came from and where the negative in the numerator came from. Thinking about number 3, what do I take the derivative of to get negative sine of x? Well, cosine of x. What do I take the derivative of to get 1x? What do I take the derivative of, or what do I include on every answer here when we are doing anti-differentiation? We include plus c. And then number 4, each of the exponents should increase by 1. So x squared should become x to the third. X should become x squared. 1 should become x. I should always have a plus c. But since there are no numbers in front of any of these variables, I also need to divide by that exponent, because if I have x to the third over 3 and then I move the 3, when I differentiate, those two 3's would divide out. So important to notice when we're just talking about pieces of a polynomial, we're adding 1 to each of our exponents and we're dividing by that same exponent. So let's formalize some of this a little bit more. Instead of just thinking and using what we know, let's formalize some rules and some definitions. So an indefinite integral, which is this symbol right here, this symbol that kind of looks like a funky looking S, this is the symbol for integral. And when we see that integral, it tells us that we are going to integrate, and we're going to integrate with respect to whatever variable is identified here. So dx is telling us we are going to integrate with respect to x. Something important to notice, this is called an indefinite integral because there are no bounds. We will talk about in future chapters, well, what happens if there's actually numbers on the top and the bottom of that integral? How can we use those numbers to evaluate an integral in a different way? So for right now, we're talking about an indefinite integral, which means we don't have bounds. We don't know, we're integrating over some variable. So with respect to some variable, with respect to x. And then I think it's really important to see what this is saying in and of itself. It's saying if I take the integral, or if I integrate the derivative with respect to x, I get the original function plus some potential constant value. So let's formalize those rules now. One of the things that we talked about on examples 1, 2, and 3 up top was, or 1, 2, and 4, I should say, was that when we have a polynomial, when we're differentiating, we're decreasing the exponent by 1 and moving it to the front. So to integrate, or to do the opposite of that, we're going to do exactly the opposite of that. We're going to increase our exponent by 1, and we're going to multiply by the reciprocal of that exponent. So just like on number 2, we increased the exponent by 1 to get -2. We then also divided by -2. So increase the degree by 1 and divide by that same degree, or multiply by the reciprocal. The constant rule, and we saw this come into play in numbers 3 and 4 up top, if we just have a number when we integrate it, that number gets a variable. And this goes with the power rule, right? If I have x to the power, if I have 2x to the power of 0, which really is the same thing as just 2, if I increase this exponent by 1, I'm now going to have 2x. So when you have a scalar, or sorry, when you have a constant, that constant gets an x. When you have a scalar, that scalar is really not related to the function. So you could actually pull the scalar out in front and multiply it at the very end as well. So that's where you're seeing it's coming, we're dealing with f of x and then multiplying by k at the end. All of the rules that we learned for trig still apply. So this is actually really not new. It's just backwards now. So last unit we talked about how we go from here to here when we differentiate. Now we're saying when we integrate, we go this way. But all of those rules, we know that the derivative of sine is cosine, so it should make sense that the integral of cosine is sine. We know that the derivative of cosine is negative sine, so similarly all of those rules apply in reverse. So let's look at some examples. I recommend that you pause this video, you work through as many of 1 through 6 as you can, and then you unpause and watch me go through each of these problems. So number 1, I'm going to use the power rule. I'm going to increase the power of this exponent by 1. That's going to give me x to the 4th. And then I'm also going to divide by that power. Don't forget your plus c. Number 2, so some of you, if you have taken calculus before, are looking at number 2 and you're trying to think through some sort of U substitution or special rule. We haven't learned anything except for these rules up here. So what you should be thinking is, how can I manipulate this function in a way that I can use the stuff that I already know? Well, I know that cosine over sine is really the same thing as cotangent. And then I'm still going to have a 1 over sine in the bottom. Don't forget your dx when you're rewriting. But 1 over sine is really the same thing as cosecant. So this is cotangent of x times cosecant of x dx. And then looking up, this is one of those that we're supposed to know. Cosecant of x times cotangent of x. When I integrate this, I'm going to get negative cosecant of x plus c. For number 3, I'm just going to use the power rule. So I'm going to increase t to the 4th is going to become t to the 5th over 5. T is going to become t squared over 2, or 1/2 t squared. Minus 5 is going to become minus 5t plus my arbitrary constant. It's basically a placeholder because we don't know if there is a constant in the original function. So if you watch me go through those and you haven't done 4, 5, and 6, pause them and see if you can work through them. So I'm going to rewrite number 4, 3x to the negative 2nd minus x to the negative 1/2, so that it becomes easier for me to use the power rule. So I'm going to increase my exponents by 1. So negative 2 plus 1 is going to give me negative 1. So 3x to the negative 1st power, and I'm going to divide by negative 1, so I'm just going to make that a negative. Minus, if I increase my exponent with x by 1, I'm going to get x to the 1/2 power, and I'm going to divide by 1/2 or multiply by the reciprocal. That's going to give me a negative 2, or a 2 in front of my x here. And then don't forget your constant. On number 5, I recommend that you split this up into 2 fractions and then simplify. Now we can integrate using the power rule. So if I add 1 to negative 3 over 2, I'm going to get negative 1/2. So I'm dividing by negative 1/2, or I'm multiplying by negative 2. Negative 2x to the negative 1/2 power. Minus, if I add 1, I guess I could say plus, but it's going to become a minus. If I add 1, I get x to the negative 1st power divided by 1. So negative x to the negative 1st power plus c. And then the last one on this page, so the 2 in front of cosine is really not doing anything at all. So I'm asking myself, what do I take the derivative of to get cosine? Well, that's going to be sine. So I'm going to just keep my 2 in front of sine, 2 sine of theta. What do I take the derivative of to get negative sine? Well, that's just cosine. So minus 3 cosine theta plus c. So we've come up with a way to work backwards from a derivative to get to an antiderivative, but every single answer that we've talked about on the front of this sheet of notes has a plus c in it. So something that should be coming into your mind is it possible for us to be given another piece of information that allows us to identify what that c value is? And the answer to that question is yes. So what we're going to talk about now is how do we deal with an integration problem, or how do we deal with anti-differentiation when we are given an initial condition, and how do we use that initial condition to solve for our particular function. So if we know a point on f of x, then we can solve for the exact value of c given those conditions. So what you're going to do is the same first couple things. You're going to integrate, and you're going to make sure you have plus c. Then you're going to substitute in your initial condition so that you can solve for c. So let's look at some examples involving this. If I want to know the original function and I'm given a derivative, what I'm going to do is I'm going to integrate that derivative. So I'm going to take the integral of f prime of x dx. This is going to give me my original function f. So f of x is going to equal that integral. So I'm going to integrate x to the negative 3rd power dx. So I'm going to add 1 to the exponent and divide by that exponent. That gives me x to the negative 2nd divided by negative 2, or negative x to the negative 2nd divided by 2 plus c. That is my f of x. But now we are given an initial condition. We know that when x is 1, f is 3 over 2. So since we know that f of 1 is 3 over 2, we can say that 3 over 2 equals negative 1 to the negative 2nd over 2 plus c, which is going to give us that c itself is actually 2. which means we can rewrite our function now. F of x is equal to negative x to the negative second over 2 plus 2. So we actually did find the exact function because we were given an initial condition. The last thing we're going to do is we're going to tie this back to the relationship that exists between position, velocity, and acceleration. So what we learned early on is that with differentiation, we go from position to velocity when we take the derivative to acceleration. So if we have position, we take the derivative, that gives us the velocity. If we have velocity, we take the derivative, that gives us acceleration. Now, if we're looking at integration, this works in the exact opposite direction. So with integration, if we have acceleration and we integrate it, we get velocity. If we have velocity and we integrate it, we get position. So that relationship still exists, but now we have a new way to connect them. So the integral, for example, of acceleration is velocity plus the initial velocity, right? The velocity function plus some c value, but we know that that c value is just going to be v naught, the initial velocity. The integral of the velocity function is going to give us the position function plus the original position, s naught. So let's go ahead and look at a couple of examples and work through this process specifically in terms of acceleration, position, and velocity. Given that the acceleration of a particle at time t is the function 4t minus 3, we're also given a velocity and a position condition or value. Determine the equation for the position of the particle. So the very first thing I need to do is I need to take my acceleration and I need to integrate it, or I need to use anti-differentiation in order to find the velocity function. So what I'm saying is I want to take the integral of 4t minus 3 with respect to t, and that's going to give me, I'm going to increase the exponent by 1, that gives me squared, and divide by that. My 3 is going to get a t, and I'm going to add a c value. So I know that my velocity function is 2t squared minus 3t plus c. But since we have this information that when x is 1, or when t is 1, velocity is 6, we can substitute that in to figure out exactly the value of c. So when we do this, we're going to get that c equals 7, which means we can rewrite our velocity function 2t squared minus 3t plus 7. So here's our velocity function. Now we're going to follow the same basic process to find our position function. So the position function is going to be the integral of the velocity function with respect to t. So we're going to integrate 2t squared minus 3t plus 7 with respect to t. And again, we can simply use the power rule to integrate this polynomial. So I'm going to add 1 to t squared. That's going to give me t to the third. So I have 2t to the third, but then I also have to divide by that 3. Minus, I'm going to add 1 to t to the first power to get t to the second power, and I'm going to divide by that 2, plus 7t plus c. This is my position function. And now I can take this condition that I was given, that when t is 2, the position is 5. So 5 equals 2 times 2 to the third over 3 minus 3 times 2 squared over 2 plus 7 times 2 plus c. I know you're capable of simplifying that. I'm going to tell you that c is equal to negative 25 over 3. And I actually did something that I want to point out. Right now in this problem, I have 2 different c's representing 2 different numbers. So if I'm going to be correct and not lose points somewhere, I need to go back and give at least one of these c's a subscript so that I'm indicating that they are not the same value. And that was a faux pas on my part, but I'm correcting it right there. So anytime, if you have 3 C's at some point in a problem, you can call them C1, C2, C3. I could call this one over here on the left C1, but I'm just going to leave it as C and call you second one C1. So the position function is going to be 2t to the third over 3 minus 3t squared over 2 plus 7t minus 25 over 3. And I apologize, that got a little scrunched and it's hard to read. 25 over 3 is that last number. Okay, last question, number 8. Given that on Earth, in America, the acceleration of an object due to gravity is approximately negative 32 feet per second squared. Given the acceleration, determine both the velocity and position equations for a particle in free fall. So we know that velocity is the integral of acceleration, and in this case we are told that acceleration is negative 32, and we're going to differentiate with respect to time. That means that our velocity function is negative 32t plus some c1 value. And actually, instead of calling it c1, I'm going to call it v0, because that's really what it is. It's the initial velocity of the object, whatever that object happens to be. So there's our velocity function. Now we can integrate our velocity function to get our position function. No, you do not have to write and set up that the integral of velocity is position each time. I'm just showing you that because if this is the first time you're seeing this, I really want you to get this relationship between these two things. So position is going to be the integral, or we're going to integrate velocity to get the position function. So I'm going to insert our velocity function here, integrate it with respect to t. So position is going to be negative 32t squared divided by 2, which is really just negative 16t squared, plus v0, which is now going to have a t on it, plus c, or in this case, we're just going to call that the initial position s0. So we now have our velocity function and our position function based on that given acceleration function. So key things to remember about this section: anti-differentiation or integration is the opposite of taking the derivative. So it's the inverse operation of differentiation. Remember that we can use the power rule, adding 1 to the exponent and multiplying by 1 over that exponent. The constant rule, every constant when we integrate it gets a variable. And the scalar rule, that scalar just kind of hangs on for the ride. And then also remembering those different trig functions that we learned when we learned differentiation and how those all come to play when we are integrating. And then lastly, now that we know this term integration, how we can use that to form a new relationship with acceleration, velocity, and position. Looking forward to helping support you in class. Thanks for listening.